In this demonstration, we will show some experiments we conducted for our recently published paper, Securing xApps in Open RAN. We can start with a brief introduction to Open RAN. Open RAN basically refers to the disaggregation of hardware and software within the radio access network. This was first introduced by 3GPP's Technical Report 38.801. It introduced the horizontal disaggregation in radio access network. Right now, this movement is led by Open RAN Alliance, who have defined standard and open interfaces and specifications for this movement. Few of the benefits of Open RAN are: Open RAN is built using commercial off-the-shelf hardware, and it promotes open and standardized interfaces, which promote the use of multi-vendor RAN deployments, which means it removes the vendor locking. And also, it tries to accelerate the innovation in RAN by using the third-party apps. And also, it tries to reduce the capital expenditure and operational expenditure using a cloud-native approach. So in this work, we propose a hierarchical approach. So here we can see we have taken a layer-specific monitoring approach. That means we have divided these third-party applications based on their control loops time scale. That means RApps are having the highest control loop duration and DApps being the shortest. So here we have assigned dedicated apps to measure the security at each level. So we think this is a more resource efficient approach because if we need to process more data, we can do it at higher levels where more resources are available. In order to evaluate our experiment, we have developed two experimental setups. So in the first one, we have developed our authentication server and xApps, everything inside the near real-time rig. Whereas with setup 2, we have placed the authentication server inside non-real-time rig, and xApps are still residing inside the near real-time rig. So the purpose of this was to compare the performance when the authentication server is placed at the same level and one level above. In this work, we have used JSON Web Tokens, or called JWTs, to provide access and communication between xApps. Here, the XRF server, which acts as an authentication server, gives these tokens to different xApps who need to communicate with each other. So here we have several different types of tokens, such as access token and refresh tokens. Access tokens are usually short-lived, whereas refresh tokens are longer-lived. So as you can see in this diagram, we can use refresh tokens to get new access tokens. This is more efficient rather than doing the initial authentication because it consumes less time and it is efficient. Refresh tokens comes with some drawbacks, such as how we are going to securely store and transmit them. Usually we can use TLS for secure transmission, but still there's a problem how we are going to store them securely. Because JSON Web Tokens are self-contained, that means the server does not keep track of the tokens. There's no way for server to know if this refresh token is presented by a legitimate user or a malicious user. Therefore, we can use mechanisms like refresh token rotation to provide some protection against this. As you can see in this diagram, when we use refresh tokens, the server keeps track of some tokens that are used to take new tokens. That means server keeps a track of linkage between the tokens. Now we can show a small demonstration on how xApps are going to communicate using the JSON Web Tokens. Now we have a running authentication server, and then we have the xApp2, which acts as a resource, and then xApp1, who will be the client, is going to communicate using these tokens. So here we can see xApp1 can communicate successfully using these tokens, and we can see from the server logs that it has obtained the token, and there was a token refresh log, and also we can see from the server that there has been some error. That means when it receives a access request with the expired token. It gives this error message. At that time, the except one client try to get a new access token via the authentication server. So we can see these refreshes in the server log. So in our experiments, we have taken several time measurements. One of those is the authentication delay. So here we have defined three cases. That means we have three types. In one case, we will only use the access tokens, and another one we will use access tokens plus the refresh tokens. And in the third scenario, we will use the access token plus refresh token with token rotation enabled. And we have conducted experiments for these three cases under both setups. That means we have 6 graphs. And based on the results, you can see in these illustrations, it is clear that setup 2 has consumed more time. That means when we have placed the authentication server at the non-real-time rig. We have also conducted an experiment to measure the network bandwidth consumption. As you see in this diagram, when we only use the access token, it has the least consumption. But it is a very basic form and it takes a lot of time to get new access tokens. And when we use refresh token, it consumes some additional bandwidth because now server has to issue 2 token types. And when we enable the refresh token rotation, it consumes the most bandwidth because there are some extra messages because the server now keep track of these all refresh tokens. But this provides the most secure mechanism against token hijacking. We can explain how the token rotation is going to provide protection against token leakage in our xApps environment. So here we have a malicious xApps who has a hijack token. And as you can see in this diagram, once the legitimate xApps requests a new access token, the server is going to invalidate the old token and also it's going to keep track of this. And when the malicious user is trying to get a new refresh token, use the token it hijacked, the server can detect this reuse. That means server detect that same refresh token is used by 2 users to get a new token. When server detect this, the server invalidate both refresh token 1 and refresh token 2. That means now both the malicious user and the legitimate user can't access the resource because they are in the same token family. We can demonstrate this token reuse detection using a small experiment. So here we have a running xApps 1 which communicate with xApps 2. And now we are going to give the leaked token or hijack token to the malicious client. And when we launch the attack, the server immediately detects it, as you can see in the server log, and also the malicious user get the response that so the server has detected a security breach. So in the server log you can see this error message, and also you can see there's a additional error message on the server log that is for the legitimate user. So if we have a closer look at the logs, so this is the log of the malicious user. We have the token, hijack token, which we use to launch an attack. And if we look at the server log, we can see this is a token which was previously used by the legitimate app and it got 200 OK response. But now when the same token is used by the malicious user, it got an error message. And also you can see there's a error message adjacent to that response. This is for a different token, but this is for the legitimate xApps because these two tokens are connected because the old token was used to derive the new token for the legitimate xApps. When the server cancels the whole token family, the legitimate user's access is expired because the server assumes this token family is no longer secure. So now the legitimate xApps has to re-authenticate. We have also taken some measurements to show this token reuse detection. Here we have a graph which shows some blue dots and red dots. So these red dots are the instances where we have detected token reuse detection. We have these clear visible spikes because it consumes more time because the server forces legitimate user to re-authenticate, which consumes more time than using refresh tokens. This is the end of our demonstration. Thank you for listening.